In this part, we will learn about the random variable and probability distributions. Random variables give numbers to outcomes of random events. The outcomes of some random experiments may not be numbers. We usually use upperclass letters like X and lowercase letters like X to denote their values. Here is a random experiment to observe the sum of possible outcomes when two dice are rolled. We have the sample space S on the letter I, J respectively represent the outcomes of the first dice and the second dice. We can represent the random variable X in this way. Random variables can be divided into two types based on the possible values. A random variable that may assume only a finite number or an infinite sequence of values is said to be the discrete random variable. For example, the number of births in a certain place in a certain year, the age in one group. So, what is the continuous random variable? One that may assume any value in some interval on the real number line is said to be continuous random variable. For example, the continuous prices, the amount of milk a cow produces on a given day. It may be a value in a given interval of numbers. Given a random variable, we often compute the expectation and variance, which are two important summary statistics. Expectation describes the average value. We have two ways to represent the expected value of the discrete random variable and continuous random variable. The formula of the discrete means that we multiply each value x in the support by its receptive probability p, and then we add them all together. It can be seen as an average value, but weighted by the likelihood of the value. As for the continuous random variable, fx dx represents the probability that x is an infinitesimal range of width dx around x. Thus, we can interpret the formula for ex as a weighted integral of the value x, where the weights are the probabilities fx dx. The expected value is also called the mean or average. The variance describes the spread around the expectation. In other words, it measures the gap between the random variables and their expectations. So the formula is the expected value of square of x minus its expected value. X star is the standardized variable of x. X has been rescaled to have the mean and its standard deviation. Apart from the expectation and variance, there's a new concept, covariance. Covariance is a measure of how much two random variables vary together, like the height of a person and the weight of a person in a population. The covariance of two random variables, x and y, is given here, where n is the number of samples, like the number of people, and x bar, y bar are the mean of the random variable xy, represented as a vector. With covariance, we can calculate the entries of the covariance metric, which is a square metric given by C. where D describes the dimension or number of random variables of the data, like the number of features like height, width, weight. For example, we have the two-dimensional case, but it can be easily generalized to more dimensional data. Following from the previous equations, the covariance metric is given here. We can calculate each element by this formula. The covariance metric is symmetric, since the sigma yx is equal to the sigma xy. The probability distribution for a random variable describes how the probabilities are distributed over the values of the random variable. For any discrete random variable x in the sample space, we have associated probabilities. The probability distribution is defined by a probability mass function denoted by the fx. This function provides the probability for each value of the random variable. We also have the cumulative distribution function, CDF. It indicates the probability that x falls into the interval less than or equal to x. In the development of the probability function for a discrete random variable, two conditions need to be satisfied. There is the countable number of possible values. The second one is the sum of the probabilities for each value of the random variables must equal to 1. Two of the most widely used discrete probability distributions are binomial and Poisson. Binomial distribution consists of n repeated Bernoulli trials. When n equals 1, binomial distribution is a Bernoulli distribution. Binomial probability mass function is defined here, where C is known as the binomial coefficients. K is the number of success trials. M is the total number of independent experiments. Parameter P is the discrete probability distribution of the number of success in a sequence of m independent experiments. It has its own Boolean value outcome, success with probability P or value with probability 1 minus P. There is a figure showing the probability distribution of the number of success during these 10 trials, and the probability equals 0.5. The Poisson distribution is a discrete distribution that measures the probability of a given number of events happening in a specified time period. In the Poisson distribution, the probability of all the possible values of a random variable x can be written as this formula. The parameter lambda represents the average during an interval. For example, the number of survey requests received by a survey center, the number of passengers waiting at a bus stop, the number of faults that occur in the machine, the number of times that a neutral disaster happens, and the number of variations in the DNA sequence. The Poisson distribution is an extreme case of binomial distribution when n becomes very large and probability gets very small. It is challenging to figure out when to use the binomial distributions or Poisson distributions. So here comes the experience. If we are given an exact probability and we want to find the probability of the event happening at a certain number of times out of x, like 10 times out of 100 or 99 times out of 1000, then use the binomial distribution formula. If the question has an average probability of an event happening per unit, like the per unit of time circle event, and we want to find probability of a certain number of events happening in a period of time, or the number of events, then we can use the Poisson distribution. So we can see the Poisson distribution describes the number of times that a random event will occur within an interval. We can apply the Poisson noise for images for data augmentation in the image processing tasks. Poisson noise that follows the Poisson distribution usually occurs due to the uncertainty caused by the image equipment. Here is the summary of the discrete distribution. For different conditions, we can see the check of each distribution. For example, after several Bernoulli trials with replacement, and if we define the number of success in n trials as probability p, then we have the binomial distribution to follow. A continuous distribution describes the probability of the possible values of a continuous random variable. A continuous random variable is a random variable with a set of possible values, known as the range, that is the infinite and uncountable. In the continuous case, the counterpart of probability mass function for discrete random variables is the probability density function, PDF, also denoted by the fx. It is defined as the area under the curve of its PDF. It is sometimes useful to consider the cumulative distribution function in terms of the PDF, representing in this formula. It is the probability that the variable takes a value less than or equal to x. We now explore how probabilities concerning the continuous random variable x related to its PDF. The important result here is the formula P. Different from the discrete distributions, there are infinite numbers of possible values, and for the probability density function, the integral over all values of the random variable must equal to 1. Here we have the figures to compare the probability function and cumulative distribution. The up to figures are for the discrete random variables, and the following two figures are described by continuous random variables. T and F over here is applicable for the discrete random variable. Like throwing a dice, we can only select 1 to 6 numbers, which is countable. And the PDF is for the continuous random variable. The area under the graph of the fx corresponding to some interval obtained by computing the integral of fx over that interval. It provides the probability that the variable will take on a value within that interval. The cumulative distribution function is for describing the distribution of random variables. Either it is continuous or discrete. As we can see from the figure, the CTF for discrete random variable is also discrete. When x is equals to 3, then we can get the 0.6, which is the sum of the fx. When x is equal to the 1, then we can get 0.1. When x equals to 2, then we can get the fx 0.2. And so we can get the 0.3 when the x is 3. So we sum up all together is the 0.6. The CDF for the continuous random variables is to find the probability lies in any intervals x2 to x1. A widely used continuous probability distribution in statistics is normal probability distribution. The normal probability distribution is a well-shaped curve like this graph. We can say any continuous random variable x follows normal distribution if probability density function fx is calculated in this formula. The formula is with the mean mean and also the standard deviation sigma. And also when the mean equals to 0 and sigma equals 1, the random variable x is said to follow the standard normal distribution. In summary, the distribution of data is how often each observation occurs, and can be described by its central tendency and variation around that central tendency. There are many other discrete and continuous probability distributions. Other widely used continuous distributions include the exponential, gamma, and some others. And the other commonly used discrete distributions include the negative binomial, multinomial, and so on. Here is the example of image processing. We add some Gaussian and Poisson noise to the original images to augment the dataset, like shown in these figures. A Gaussian noise is a type of noise which is in the form of Gaussian distribution, setting the mean to 0 and the sigma to 10, such as the white noise commonly encountered. The second image, we add some Poisson noise. It is noise assuming each pixel in the image is drawn from a Poisson distribution of parameter lambda. Here we set the lambda is 15. The lambda is the mean of the distribution, but also its variance. So why we add the noise to input image? Well, it will improve the model generalization performance since it expands the size of the input training samples each time a training sample is exposed to the model. Random noise like Gaussian or Poisson is added to the input variables, making them different every time it is exposed to the model. In this way, adding noise to input samples is a simple form of data augmentation.